Welcome back. We are picking up with our second gas law, Charles's law, looking at the effect of temperature on gas volume. And the French scientist Charles, hence the Charles law, discovered that the volume of a fixed quantity of gas at a constant pressure decreases with decreasing temperature. Now Charles saw that as the temperature increases, the volume increases because the faster molecules collide harder and push each other further apart. We can see here that I have a certain volume of gas and it's at a certain temperature. Then I added heat and those particles start moving faster as the temperature increases and it pushes that plunger up, so it increases the volume. We can see here that we have a direct relationship. The last one, Boyle's law, was an inverse relationship. As the pressure increased, the volume decreased. Here I have when the temperature increases, the volume also increases. When we're looking at this law, here's our equation. V1 over T1 equals V2 over T2. Having a constant number of particles, we're not increasing our number of particles, and we're not changing the pressure, so that's at constant moles and pressure. Now, big thing to note, your temperature must always be expressed in Kelvin. So if you have degrees Celsius, you need to add 273.15. Let's look at a quick demo.
Hey folks, it's Dr. D here. In this demonstration, we're going to be looking at Charles's law, one of the gas laws. Charles's law relates the volume of a gas to its temperature. So the way that we're going to do this demonstration is we're going to use some liquid nitrogen. So I've got some liquid nitrogen right here in this container. This is called a dewar. It's like a really big fancy thermos. And I'm going to go ahead and I'm going to put on some special gloves to do this because liquid nitrogen is very cold. So it is minus 196 degrees on the Celsius scale or 77 degrees on the Kelvin scale. So that's 77 degrees above the absolute coldest temperature possible. So let me go ahead. I'm going to pour that liquid nitrogen here into this other dewar so that you can see what's going on. Now, one of the things that you might observe there in that dewar is it looks like it's boiling, and in fact it is boiling because the temperature of that dewar is so much warmer, right? It was room temperature compared to the temperature of the liquid nitrogen that I'm pouring in there. Now, nitrogen, by the way, is about 80% of the atmosphere that we breathe, so it's most of the gas that is around you right now. All right, so I'm going to get this poured in there. We're going to allow it to stop boiling a little bit just so that it's easier for us to see. Okay, so now the next thing that we're going to do to demonstrate Charles's law is we're going to put some balloons into this liquid nitrogen. So I've got a balloon here, and what we're going to do is we're going to put this balloon into the liquid nitrogen and see what happens. We like to call these a portable air container, right? Portable gas container. So let's go ahead. Now the temperature of this gas right now is the temperature in this room, which is about 24 degrees Celsius at this point. And what we're going to do is we're going to see what happens. So you'll see already that the volume of that balloon is decreasing dramatically. And in fact, it looks like it completely, all the gas completely is gone. It's what it looks like. In fact, it's not gone. It is just reduced in volume. So if I take this out and we look at what happens to it when we warm it back up, here I'll hold it so we can watch. We're going to see that as that gas warms back up, that in fact it was still in the balloon, and it's going to refill the balloon, so it's going to return to its original volume, the volume that corresponded to the temperature in this room. Okay, so there we go. So Charles's law. Now, just to have a little bit of fun, I've got a few balloons. So we're going to see how many balloons we can stuff into this container of liquid nitrogen. So here we go. Now let's warm them up.
Now, a little word of warning when you're doing your temperature conversions. If I have 25.0 degrees Celsius and I add my 273.15, I would get 298.15. But my original was to the tenths, so I need to finish to the tenths. That 5 will round that 1 up to a 2. And if I have 323 Kelvin, I need to finish significant to the ones. So 323 minus 273.15, that would be 49.85. Again, when you're adding or subtracting, you go to the most common integer, which would be the ones in this case. That 8 will round that 9 up to a 50, so 50 point. Let's do a sample problem. A sample of carbon dioxide in a gas-tight syringe has a volume of 25 milliliters. That's a volume for my initial volume, so I'm going to call it V1. At room temperature, which is 20 degrees Celsius. So my temperature at that volume is 20.0 degrees Celsius, and I'm just going to put plus 273.15 right next to it. We'll do that math in a second. What is the final volume, V2? We don't know. If the gas in the syringe is raised to a temperature of 37 degrees Celsius, so my T2, 37 degrees Celsius plus 273.15. Let's get those temperatures converted first. All right, and you should have gotten 293.2 Kelvin. Make sure that there is a decimal point after that 0 showing that we are significant to the ones. Now we're going to set it up. V1 over T1 equals V2 over T2. I know my V1 is 25.0 milliliters. My T1, 293.2 Kelvin. My V2 is question mark. My T2 is 310. Now I don't know about you, I don't love working with fractions. I like linear problems. So to solve this, I'm going to cross multiply and set it equal to that cross multiplied. So I'm going to rewrite this and say 293.2 Kelvin times V2 is equal to, and then I'm going to plug into my calculator 25 times 310 to get 7750. Now I can look at this and I can go, oh, to solve for V2, I need to divide both sides by 293.2. And when I plug that into my calculator, I should get 26 milliliters. Let's see if it makes sense. My temperature went from 20 degrees Celsius to 37 degrees Celsius. So my temperature increased. And according to Charles' law, if temperature increases, the volume should increase. Volume went from 25 milliliters to 26 milliliters. So the volume did increase. In the book, tells us that our answer was 26.4 milliliters, so I think I had a typo, and I'm pretty sure our temperature was 37.0 degrees Celsius, giving me 3 sig figs, because that would give me the 26.4 if I hadn't rounded to 2. Why don't you see if you can set this question up? Did you get the correct variables? Our V1 is 5 milliliters, and our temperature 1 is 22 degrees Celsius. And then it says it's immersed in an ice bath, which is 0 degrees Celsius, so that's our T2. It wants to know the new volume, V2 question mark. We're going to set up our V1 over T1 equals V2 over T2. Now if you would rather, like I cross-multiplied the last time, if you would rather start off cross-multiplied and say that T1 times V2 is equal to V1 times T2. That's fine too. Just make sure you don't get those 1s and 2s mixed up. So I'm going to start off this way, just as something different. T1, so I'm going to start with that 22 degrees Celsius, and whoops, we need to get to Kelvin. Once I change to Kelvin, my T1 times V2 is on one side. It doesn't matter which side. So my T1, I had 295 Kelvin times V2, that's my question mark, is equal to my other pair, V1, which is 5 milliliters, times T2, which is 273 Kelvin. Now, let's give V2 by itself. So I need to divide both sides by 295K. I'm going to end with two significant figures because that 5.0 milliliters is 2 sig figs, and I should get 4.6 milliliters for my second volume. Let's make sure it makes sense. My temperature went down from 22 to 0. So if T decreased, that means my volume must decrease. My volume started at 5 and it went down to 4.6. Yes, it did decrease. I have two more practice problems for you. See if you can set this one up. Let's see if you labeled everything correctly. Our syringe that contained 12 milliliters of dry air at 25 degrees Celsius. So I'm given a volume and a temperature that go together. It's heated to 100 degrees Celsius. So I'm given a new temperature. It wants to know the volume at that new temperature. So our V2 is our question mark. Let's set it up. I'm going to use Charles's law. V1 over T1 equals V2 over T2. And then I'm going to cross multiply because fractions freak me out. So I'm going to say 298 times V2 is equal to 12 times 373. And 12 times 373 is 4,476. And to get V2 by itself, I'm going to divide both sides by 298. And it looks like I am limited to two significant figures based off of that 25 degrees Celsius. So my V2 should be 15 milliliters. Again, let's double check to make sure that we didn't make a goof. Our temperature went from 25 degrees Celsius to 100 degrees Celsius. So our temperature increased, which means our volume should increase. It went from 12 milliliters to 15 milliliters. Yes. Why don't you try this last one? See if you can set it up. As I was reading this, it said the balloon is inflated with helium to a volume of 45 liters. So that's a volume that I'm starting with, so I call it V1. At a room temperature of 25 degrees Celsius, that's the temperature that goes with that volume. If the balloon is cooled to -10, which is a new temperature, T2, what is the new volume? So we need to find V2. Let's set it up. Charles's law says that V1 over T1 equals V2 over T2. Our V1 is 45 liters over, now let's get this to Kelvin. That would give me 298 Kelvin. Our V2 we don't know, but our T2 we need to do -10 plus 273.15. That would give us 263 Kelvin. Let's cross multiply to get 298 times V2 is equal to 45 times 263, which is 11,835. To get V2 by itself, I need to divide both sides by 298. That'll cancel that out, and it should give me 39.7, and we're looking at two significant figures. I'm going to round that up to 40 liters. Again, let's make sure that we didn't goof something up. Our temperature went from 25 to -10, so our temperature decreased. Our volume must also decrease. 45 to 40 is a decrease in our volume. Good job. Now we have our third gas law, Gay Lussac's law. And he found that the pressure and temperature are related. That if the temperature increases, the average speed of those molecules increase. So more collisions result in a higher pressure. Again, this is a direct relationship. If temperature increases, pressure increases. And this formula looks very similar to our last one where we said V1 over T1 is equal to V2 over T2. And this is where we're going to go when we combine gas laws, but we're skipping a little ahead. Let's keep focusing on this. Here is our normal container under, let's say, normal temperature, and we can see these particles moving around, exerting a pressure as they hit the walls of the container. Now we're going to add heat, and those particles start moving around much faster, hitting the walls of the container with more force, increasing that pressure. Let's look at a quick demo.
Air pressure. I want to crush something. It's supposed to be open.
Yeah, I guess you're right.
Air pressure is the amount of force that gas particles exert on their container or environment.
The equipment and ingredients you're going to need for this episode include an empty can,
A large bowl,
a set of tongs,
some water,
and a stovetop. The first step in our experiment is to take some cold water and fill up our bowl.
The second step of our experiment is to pour about 100 milliliters water into the can. Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Let's look at this experiment a little closer. Before we heat our can, it's filled with liquid water and gaseous air molecules. Heating our can adds energy to our liquid water. The more energy we give our water molecules, the more excited they get, and the further apart the molecules spread. Once enough energy has been added to our liquid water, it changes state from a liquid to a gas. This gas is called water vapor. As our water vapor fills our can, it presses against the sides of our can, creating an increase in pressure. When we place our hot can upside down in our cold water, all the water vapor molecules that fill our can get really close together and turn into a few drops of liquid water. This liquid takes up a lot less space than a gas. Water in its liquid state doesn't exert nearly as much pressure on the inside of the can as it did in its gaseous state. At this point in our experiment, the outside atmospheric pressure is much higher than the pressure inside the can. In nature, pressures want to be balanced or in equilibrium. This imbalance causes the can to violently collapse, creating a balance between the pressure inside and outside of the can. This violent collapse toward the center of the can is called an implosion.
Let's do a Gay Lussac's law example. We have a steel container of nitrous oxide at a pressure, because it's in atmospheres, of 10.4 atm, so that's our P1, and it's cooled from 33 degrees Celsius, so that's our initial temperature, to negative 28 degrees Celsius, that's our second temperature. What is the final pressure? What is P2? First thing I see when I see temperature in Celsius, I need to get it to Kelvin. I'm going to add 273.15 for both of these. All right, I wrote out all of my variables in the Kelvin temperature. Let's set it up. We said P1 over T1 equals P2 over T2. I'm going to do my P1 as 10.4 atms over T1, 306 Kelvin, equals P2 over T2. Again, I don't love fractions, so I'm going to cross multiply and say 306 times P2 is equal to, I'm going to multiply 10.4 times 245, and that gives me 2548. And to get P2 by itself, I'm going to divide both sides by 306. And with two significant figures, I should get 8.3 atms. Let's make sure that this makes sense. Our temperature went from 33 to negative 28, so our temperature went down. Our pressure should also go down. Our pressure started at 10.4 and went to 8.3. So our pressure went down as well. Good job.